Hi, Mitch Winger back with another video on data analytics and machine learning. In this video, we'll talk about the basic mathematical functions we use for classification. Hope you enjoy. Okay, let's get started. You'll recall that when we build a decision tree, we partition the dataset using lines that are perpendicular to the attribute axes. The decision boundaries generated by the tree algorithm create regions, each of which should have similar target values. At least that's our goal. As you'll recall, we can use entropy to measure the similarity or homogeneity within our data set, and information gain to help us choose the next attribute to split on. We can use these decision regions to predict the target value of a brand new instance that comes our way. If it falls into the lower left region, we'll predict that it's a dot, while if it falls into the upper right region, we'll predict that it's a plus. Using this approach, the data produces both the structure of the model, i.e., which attributes to use for each split, and the parameters for that model, that is, our probability estimates in each leaf node. Now, instead of letting the algorithm choose both the structure and parameter values of the model, we can specify the structure of the model up front, but leave the numeric parameters unspecified. In this case, we can inject our domain knowledge into the process, or we can rely on data mining techniques to help us choose which attributes to include in the model. Either way, we specify the final model that will be used, including which attributes will be part of the model. The tuning process we go through to help fit the model to the data is called parameter learning or parametric modeling. Many techniques fit into this framework, including linear modeling techniques. Many of you are already familiar with linear regression, which makes for an understandable example. We still need to consider the nature of the task when using parameter modeling approaches. Is it classification, class probability estimation, or regression? And then, how do we determine whether the model fits the data well? Let's take another look at the data without our decision boundaries. What other ways could we partition the data space? If we take away the perpendicularity requirement for our decision boundaries, we can draw one line that almost perfectly splits the data. And we can use this new decision line to make our prediction instead of the multiple perpendicular decision boundaries we had in our tree model. We can even describe our decision line mathematically using our linear regression equation. So we now have a linear classifier, which is the weighted sum of the model's attributes. Our goal in regression is to minimize the sum of squared error terms in our predicted values. We call this approach an ordinary least squares, OLS, approach. We end up with a decision process that looks like this. Every linear discriminant model uses this basic approach. Of course, just like in decision trees, our decision boundary may be a plane or a hyperplane depending on the number of attributes we include in the decision function. What it boils down to, however, is that this is simply another type of supervised segmentation approach. Once we've determined the values of the weights for each attribute, we have our parameterized model. The parameter learning process tells us roughly how important each of the features is in determining the target. Parameters with a large coefficient, weight, are considered more important in predicting the target value than those with low coefficients. In fact, if the magnitude of an attribute's coefficient is extremely low, that is near zero, we actually can consider discarding that attribute. This contrasts directly with the approach of simply considering statistical significance for evaluating attributes, as is often done in academic research. Our goal in data mining is to find the attributes and their corresponding weights that will discriminate our training data as effectively as possible, with the idea that our decision boundary will be useful for predicting new unknown target values. Of course, we may transform the data, as we've discussed before we parameterize our model, but the approach we're discussing still holds for the transformed data. Now, let's look at a new set of training data. A quick glance at this data space tells us that we can cleanly separate the instances with a linear discriminant. But which line should we use? Many lines can separate these instances into pure subgroups. In fact, there are an infinite number of such lines. But the different lines have different equations and therefore represent different parameterized models of the data. Now, let's say we want to build a classifier for irises. The iris dataset is a commonly used data set in statistics classes. We're just using 2 of the iris varieties from that dataset here. So when we load the data for setosa and versicolor on a scatter diagram, we see that for the most part, they form distinct groupings with a few minor outliers and the one setosa that's right there next to all the versicolors. Our regression approach, and for classification purposes, we will use logistic regression, gives us a line that cleanly separates our classes. But is this the best line? Remember, we want to use this training data set to help us predict new values. An alternative method called support vector machine gives us a line that clearly attempts to separate the 2 groups of data, even though it misclassifies the one data point. So, which classifier is better? We'll discuss these 2 approaches in additional detail in upcoming videos. Now, sometimes we don't need a straight yes or no, setosa or versicolor prediction. Instead, we're more interested in determining which instances are more or less likely to be in one class or the other. We can estimate the probability of an instance belonging to a class. A decision tree built with the Titanic dataset would provide a good example there. Each node in that decision tree provides an estimate of surviving the voyage. Some of the decision nodes are absolutely pure, but most of them had values for each of the 2 classes, which gives us a rough estimate of the probability of belonging to each class. We can use that notion in cases where we don't need an exact prediction, but instead we would like to know which instances are more or less likely to belong to the class of interest. When using a linear discriminant, the distance from the decision line gives us a reasonably good approximation of that ranking. Similarly, we may not need an exact probability of class membership, but simply some kind of a score that tells us which instances are more or less likely to belong to the class of interest, even though we don't have an exact or even an approximation of a probability. So all of these approaches can be used rather than a strict either-or prediction value. Finally, let's consider the objective of our decision function. So remember, with regression, we want to minimize the sum of squared errors, ordinary least squares. Remember that sometimes there are many lines that can separate our data categories. The other approach we've discussed, support vector machine, tries to maximize the margin around our linear discriminator line. In essence, creating the widest space possible between our 2 data groups. In this case, we're trying to maximize that margin and therefore the likelihood that we will make a correct prediction. This maximum likelihood approach makes sense intuitively because of the notion that our training data set is just a sample of what we'll encounter when dealing with the entire population. Our primary goal is to predict for unknown data points, remember. So what happens when SVM does make a wrong prediction? That's where the margin comes in. Erroneous predictions that fall within the margin are penalized minimally or not at all. Errors outside the margin are penalized more and more severely. Predictions on the correct side of the boundary line are not penalized at all, no matter how far away they are. Obviously, if our data is linearly separable, like the example here, we just create the widest margin possible. When data points aren't linearly separable, then we have to balance the width of the margin against the penalties we have for misclassifying outside the margin. If we look at the error penalty chart for an SVM model, we see that predictions on the correct side of the boundary line are not penalized at all. If we assume the margin extends 5 units from the decision boundary, Any error within that margin is not penalized, but errors beyond the margin are penalized proportionally to their distance from the edge of that margin. This approach is called hinge loss, with the hinge occurring at the edge of the margin. By calculating different decision boundaries and margin widths, the SVM algorithm can optimize the solution for the training data set. So that's it for this video on mathematical functions for discrimination. Thanks for watching. And as always, be sure to check out the other videos in this series.